Okay, so this is the last lesson for Unit 4. So this is lesson 4.5, and we're going to talk about interpreting graphs today. So by the end of the lesson, we should be able to discuss and interpret information from various graphs that we see. So we're just going to start with the first example here. So suppose we had tap water flowing from a faucet at a constant rate, and it's used to fill each of the containers. So we want to match each of the following graphs with the appropriate container and then justify our choice. So on the first one, if we had this flask here and water is getting poured into it, okay, water's going in. The water would at first, it would get poured in pretty quickly because this is a narrow opening, so this would be fast. It would easily be able to fill up that part, but this is a bigger spot, so this would take a little while longer to fill up. So if we look at our graphs over here off to the side, right? So we have one that's just straight line, one's a nonlinear, and then one's another straight line, but it's got a lesser slope. So in this one, we have a change in speed, right? Fast to slow. So I would say that this one would be B. Goes from slow to fast. Right, so increasing, right? Filling it up, starts filling up really slowly, and then as we get to the top, it's filling up really quickly. So the next one, if we put water in the beaker here, is pretty wide. So in this case, it would fill up at the same rate, right? Because it's the same, the same diameter the whole way across, but it would take a little longer. So this would all just kind of be slow, right? So if we look at our two graphs here, right, we used B, so we've got A and C. Well, A fills up pretty quickly. C has a low, like a flatter slope. So we'd say that it's beaker C. In this one, it's just slow. We have a constant rate. So that means that it's linear. Oh yeah, this one we could say that it's non-linear. Which must mean that this graduated cylinder is graph A. Right, if we're putting the water in here, it's narrower, so that would mean that it's filling up pretty quickly, so that that steeper slope would make sense, right? So we've got this constant fast rate. And again, that one's linear. Okay. In example number 2, we had Adrian and Joseph. They decided to race each other, and then the graph showed their motion in the race. So we want to look at the graph and try to decide over what distance the race was run. So if we take a look, right, we're going to look for distance here. And then if we look at the distance, we can see that they both stopped at the same point here. So if we backtrack this all the way over here, we're at this spot right here, and then we just have to figure out the scale. So this is 150, which must mean that this is 250. And then there's 1, 2, 3, 4, 5 spaces in between here. So they were probably going up by tens, right? 10, 20, 30, 40, 50. So we would say this is 240 meters. And then we want to figure out who won. Well, who got there faster? So if we take a look, right, the blue line represents Joseph and the red line represents Adrian. So Joseph, he ran his race in 35 seconds, whereas Adrian took 40. So in this case, we would say that Joseph won. All right, part B wants to know who got a head start. Okay, well, we can look back at these lines here, right? So Adrian, he started right at 0, 0. And then Joseph, he didn't start until 5 seconds. So that must have meant that Adrian, he had the head start, right? When time started, he started moving. But whereas with Joseph, when time started, he didn't move until 5 seconds. So Adrian got a head start, and we said it was by 5 seconds. So you got a 5-second head start. Who ran faster during the race? Well, I would take a look at our lines, right? Which one is steeper? Okay, so Joseph's, his goes up a lot quicker than Adrian's does. So Joseph, he's got the steeper line. Okay. A couple more questions here. For how many seconds had Adrian been running when he was overtaken by Joseph? So we want to look at this point right here where the two lines meet. That's the point where they actually met up during their race or on their track. So at this point, they were at the exact same amount of time and then the exact same amount of distance. And at this point is when Joseph overtook Adrian. Okay, so we want to take a look at how long had Adrian been running when Joseph overtook him. So Adrian started at 0, and then at 20 seconds, he was overtaken by Joseph. And then the last one, how far from the start did Joseph overtake Adrian? So how far from the start? Well, again, we want to look at the distance. So we're looking for this spot right here. We said this was going up by tens. So this is 100 right here. So 110, 120. So at 120 meters was when he overtook Adrian. Okay. So then the next example here, we've got Chris runs each day as part of his daily exercise. The graph shows his distance from his home as he runs his route. So we want to know which segment Chris is traveling the fastest and which he is traveling the slowest in. So again, we're looking for steepness of the lines. And I would say, like, first, when they're asking about fastest and slowest, if you see any point where he stopped, I wouldn't include that because he's not technically running at that point. He's not doing anything. So we can take a look for the fastest and the slowest. So the fastest, we're looking for the steepest line. So A to B, fairly flat. B to C is pretty good. C to D flattens out again. E to F, I would probably say would be my guess of when he's running the fastest because that looks like the steepest line. The slowest, I would probably say, would be A to B. That looks the most flat. And then part B, the formula to calculate speed. Okay, recall here, speed equals distance over time. And we could short form that to V equals D over T. Okay. So then next, we want to calculate his rate of change or his speed for each segment on the graph. Okay, so I'm just going to kind of make a quick little chart here. So we've got the segment, we've got the distance in meters, the time in seconds. Oh, sorry, time is in minutes for this one. Check your graph for your units, right? And then his speed in meters per second. Okay, so for segment A to B here, so A to B, we want to look at how far he traveled. Okay. I might want to add in some more lines on my graph here, but in this case, this is so we're assuming that this is 0 here, right? They didn't put it, but we're going to assume that it is, and that this first line is 200, right? So at 200, so he traveled 200 meters. Whoops. Oh boy. Okay, there. So we went 200 meters, and then this first one was 5 minutes. So we can calculate, right? V equals distance over time. Oops, wow, I'm writing T for time. Minutes. Okay, so 200 divided by 5 is 40 meters per minute. Okay. Ooh, whoops, not paying attention here. Okay, so next segment here, I'm gonna go up a bit so we can see. So we've got B to C here. So these ones you have to be careful. I usually draw dotted lines to help me actually recognize like where I'm starting and where I'm stopping. So I'm gonna move this, put a little dot over here to where my distance was. I'm gonna put a little dot here for where my time was. So we have to figure out the scale they used. So for distance, right, we went up by 200, so this would be 200, 400, 600, 800. This would be 1,000 meters. So my distance that we went from, again, this is 200 to 1,000. So we just want this distance right here. So 200 to 1,000 is 800 meters. And then my time, well, 1, 2, 3, 4, 5, it's going up by ones. So 6, 7, 8, 9, this is 10. And again, we're going from 5 to 10. So this is only 5 minutes. So if I put this in my chart down here, oh, geez. Okay, so this is B to C. Okay, my distance we said was 800 meters and my time was 5 minutes. So V equals 800 meters over 5 minutes. And we've got 160 meters per minute. Okay. Oh, wait, draw my line. All right. So next, we're going to go up for C to D. Okay. There we go. So C to D, again, draw like your little triangle in here. It'll help you figure it out. So for distance, well, we're going to here. So again, counting by 200, so 12, 1400. And then for time, we're counting by ones, so 11, 12, 13, 14, 15. All right, so again, we're going to compare, right? So for this C to D, we just went this distance. So we went from 1,000 to 1,400. So we went 400 meters. In our time, we went from 10 to 15, so just 5 minutes. 5 minutes. All right, so then let's fill this in on our chart. Wait, yep. So we had 400 meters, and we had 5 minutes. So V equals 400 meters over 5 minutes, and we get 80 meters per minute. Oops, I forgot my 0 in 80. 80. Okay. So, maybe not yellow. How about dark purple? Maybe we can see that one. Okay, so this is going to be from D to E. So if we move back up here, so from D to E, right, this part. So no distance was traveled, right? This guy clearly stopped and took a break. So then we just have, all we care about is our time here, right? So we went from 15, 16, 17, 18, 19, 20. Okay. Oh boy. Okay. So our distance was 0 meters. Our time was still 5 minutes. So V equals 0 meters over 5 minutes. So we've got 0 meters per minute. All right, last section. Let's try, how about bright green? Maybe that color will work. So then we've got E to F. Okay, so E to F, all right, there's our section here. So again, I would draw my dotted line. Okay. So my distance, I'm still at 1,400 meters, and then I'm going all the way back to the starting point. So I went 1,400 meters. And then for my time, well, 25. So I went 1,400 meters and then 5 minutes here. Right? Oops. So 1,400 meters and 5 minutes. So my V, we're doing 1,400 over 5. Oh, and remember, I forgot this part. Because we're going back towards our starting point, right, towards the sensor, make sure that that distance is negative, right? And then 280 meters per minute. Okay, so watch out for those. Those are easy mistakes to make when you forget to put in that negative when you're going back towards the sensor. Okay, so that's the end of that question. Okay, so we're gonna move on. We've got one, or I think 2 more examples here. Okay, so example number 4, the graph represents the distance between a squirrel and a tree in meters as a function of time in seconds. So we want to calculate the speed of each section of the graph, and we want to show our work. So again, we just have to calculate speed, so we don't have to make a whole chart. We can just calculate the speed for each one. So V, again, so this is going to be for like section A here. So I'm just going to call it VA so that I can distinguish. Please try and use these little distinguishing features, right? When we put that A there, it's telling me which section you're using, or do colors, but just a way to tell me which section you're actually talking about. So for A here, right, I need my scale here. There we go. So in this case, time on the bottom, so we went 4 seconds. I'm assuming it's, oh yeah, seconds was in the question. So 4 seconds. And then the distance, well, we went up to 8, and this is meters. So we've got 2 meters per second. Okay, so switch colors. So B here. So we've got VB, right? This squirrel stopped. So we didn't go anywhere, and he didn't go anywhere for 1 second. So we've got 0 meters per second. For section C, BC, okay, so again, draw in your triangle, okay? So be careful here. So our distance, we are going from 8 all the way up to 32. Okay, so we've got 24 meters that this squirrel traveled, and he did so, right, we went from, this was 5 to 8, so in 3 seconds. So this time he was traveling 8 meters per second. Okay, so then up here, right, we've got V with, oh, we forgot a letter, so I'm just going to label this E. We've got VE. Okay, again, the squirrel stopped, so 0 meters. Okay, and did so, right, for 2 seconds. So we've got 0 meters per second. And then the last section here from, we'll call it all section D, so VD here. So we went from 32 meters all the way back down to our starting point. And now, again, we're going back towards that starting point, so watch out, your distance should be negative. And then the time it took, well, we went from 10 seconds all the way over here to 15 seconds, so in 5 seconds. So this one gives us a negative 6.4 meters per second. Okay. The last question here, I'll write in the answers, but you guys can kind of try it on your own. So you want to choose the correct graph for each bottle and explain your reasoning. For the remaining 3 graphs, so there's 3 extra graphs, you want to sketch what the bottles would look like. Okay, so I'll just kind of give you the answers here. So I'll write them along the side here. I'm going to label these. So I'm going to call this flask A, B, C, D, E, and F, and then graph 1, 2, 3, 4, 5, 6, 7, 8, and 9. So if you're actually trying to figure this out, 1 is D, 2 doesn't have 1, 3 is F, 4 is A, 5 is E, 6 is C, 7 is B, and then 8 and 9 don't have 1. So if I had to draw a container for 2, for graph number 2, I'm not a good artist, so I would probably draw something. So 2, it starts out fast and then it slows down. And this is pouring into. So starts out fast, so that's pretty bad. Alright, so it would fill this part up down here fast, and then the top it would take longer to fill up, so that's why we have that fast to slow. For 8, okay, we have this wiggly graph here, so it kind of starts out slow, goes fast, tapers off, goes slow, and then gets fast again. So, oh boy, here I go. Okay, so this bottom part would fill up slowly. We have a narrower part that would fill fast. This bigger part in the middle would fill slow and then fill fast again. Oh, sorry, this isn't 3, this is 9. And then the last one, or sorry, this is an 8. Wow, 8. And then for 9, kind of starts out fairly quickly, gets slower, and then quicker again. So something like that, right? So the bottom would fill quick, the middle part slow, and the top part fast again. Okay, so you can kind of take a look at all the rest of them if you want to on the actual filled in lesson and decide why they match up, but I'm not going to spend all of your time doing that. Okay, so make sure that you try out your homework questions and check them. That's the end of